So today I would like to talk to you about why why the simplex algorithm is not polynomial time. Okay, that means so the idea here is that we talk of when we want to talk of a complexity of an algorithm, that means we want to have an estimate of how much time it can take, computer time you can say, where we say that 1 unit of computation could be addition, subtraction, or multiplication, division also maybe. But so we say that a basic operation of calculation, we give it 1 unit of time, and then you want to count the total number of computations that will be required for the algorithm to come to a stop. And this is the kind. So when we want to measure the complexity, we actually talk. So first let me say why. So let me talk today why simplex algorithm is not polynomial time. Okay, this is the idea, and let's try to develop. So what we will show is, so normally when you talk of the complexity of an algorithm, you do the worst case analysis. Okay, so the idea here is, see, for example, in the simplex algorithm, take the instance, because we are not specifying the rule for, or the choice of the incoming variable is not uniquely specified. That means it is incompletely specified, right? It is not specified at all. So you can either, like Danzig said, you go for Cj minus Zj maximum. Well, in our case it will be so you want to maximum improvement, you go for that. But then maximum improvement, as I told you, is a more complicated computation. So you just go by the values of Cj minus Zj. That could be one rule. Or you could go for pick up any Cj minus Zj which is positive, and so on. So the entry, if the incoming variable, the choice of the incoming variable is not specified completely, then the idea would to, if you want to do the worst case analysis here, you would have to do two things. You have to come up with a class of instances, or you'll have to come up with a class of instances which are very unfortunate. That means the algorithm doesn't perform well on such which are unfortunate. Okay, and then the second thing will be that you'll have to exhibit. So here you'll have to exhibit a long sequence, an exponential sequence of pivots for which the value pivots for which the value is decreasing constantly, right? So therefore the algorithm will not stop exponential, I should say, exponential sequence of pivots for which the value is decreasing in the minimization case, and in the maximization case it will be a long sequence of pivots for which the value of the objective function keeps increasing, for which the value value of the objective function is decreasing in this case, and maximization it is increasing. So this is the two things that we have to do, and that's what Klee and Minty sat down to do. They constructed Klee and Minty because this was a question which was bothering a lot of people, and especially computer scientists and so on, to determine whether a simplex algorithm was polynomial time or not. And this was before Khashian came up with his ellipsoid algorithm. Okay, so then they Klee and Minty came up with the class of instances, and let me start building up there how they constructed this set of problems. Okay, so a d cube you have a concept of a 3 cube, right, which of course I have shown you here. The dark lines give you a 3 cube, right, and the vertices here would be 1 0 0, and this for example would be 0 0 0, and so on, 1 1 0, right. So that means so this would be a 3 cube, and so I just extend the this thing to d dimension d. So d cube, so this will have 2d faces and 2 raised to d vertices, and if you take the coordinates of any point as x d, because d dimensional, then the idea, and this has, because this has 2d 2d subsets, and for each subset what you will do is you will put the corresponding x's to 1s and the remaining 1s to 0. So that will give you 2d vertices of this polytope of this d cube, right. Okay. Now let us just extend. So the idea is that you just pull 2 corners of this d cube from here and here diagonally opposite, just pull them by a small distance, and then what you get will be a perturbed d cube. It will not be a d cube, essentially a perturbed part of the polytope, and you see that if as epsilon goes to 0, all these vertices of the perturbed d cube will collapse into the original vertices. So this is the idea. You perturb the d cube by a small amount, and the description of the perturbed, so perturbed d cube. Here let us see, the idea is that you take 0 less than epsilon less than half. So it could be any value of epsilon which is between 0 and half, and the way we will describe is that yeah, 1 epsilon x j minus 1 less than or equal to x j less than or equal to 1 minus epsilon x j minus 1. I think this should be the thing, right, and of course your x j's are all greater than or equal to 0 for all j. Okay. So this is the thing, and now consider, so corresponding to this polytope we define the corresponding LPP is, so here I will say a maximize xd, and the minus sign, normally they define it as a minimize minus xd, which actually is maximize xd. The minus sign can be outside, subject to yeah, I should have said here 0 less than or equal to x1 less than or equal to 1. For x1 it is this, and this holds for j varying from 2 to d. Okay. Yeah, the constraints include, so here subject to what we will have is that x1 is greater than or equal to 0. So here, okay, so this will become now epsilon. Yeah. For the original d cube you have xj is between 0 and 1. So here it will be epsilon less than or equal to, so therefore the first constraint will be x1 minus r1 is equal to epsilon. So I reduce it to the standard form. This polytope I reduce to the standard form, and then x1 plus, because it is less than or equal to 1, so S1 is equal to 1. This is the set of constraints corresponding to x1, and then here similarly for this one we will say that xj minus epsilon xj minus 1 plus rj is equal to 0, yeah, and xj plus epsilon xj minus 1 epsilon xj minus 1. Okay, this should be minus rj, sorry, because the constraint is xj greater than or equal to epsilon j xj minus 1. So when I bring it, it is greater than or equal to 0. To make it to 0, I have to say minus rj. So here it is less, so that will be plus sj, and this is equal to 1. Okay, and all the variables xj, rj, and sj are greater than or equal to 0 for all j. So, this is the corresponding LPP, and we will try to show you that in the absence of specific rule for an incoming variable into the basis, I will exhibit a long sequence of pivots. So, the value in this case keeps on increasing. Okay. So, the first thing that we notice about this is the first lemma. Yes, lemma 1. So, what it says is that every basic feasible solution for this linear programming problem will have all the x's present in it, right. And so, okay, so I first describe the structure of the basic feasible solution. So, every, and let me call this as problem 2. Okay, this was my description of the Polito, and this is 2, right. So, the corresponding LPP. Yes, every basic feasible solution of 2 will have all the xj's present in it, and remember this is now 2D. The number of constraints for each xj, you have 2 constraints, right, counting from x1. So, the number of constraints is 2D, and you can show that the corresponding coefficient matrix is full rank, because you have 2 identity matrices here corresponding to R1 and S1, and okay, that part we will not worry about here right now, but it can be easily checked. Okay. So, have all the xj's present in it, and only one of Rj or Sj, right. So, that means either Rj will be present in the basic feasible solution or an Sj. So, that means it makes it 2D, right, because all the D xj's are present, and then either Rj or Sj is present for every j. So, you have 2D basic variables. Okay. So, let us prove this. Simple. Okay. So, now let us see, we are saying that, yeah, from here we have that x, okay, x1 is greater than or equal to epsilon from this constraint, right, and from this one xj is greater than or equal to epsilon xj minus 1, which implies that xj is greater than or equal to epsilon j, because yeah, I think it will be j minus 1. Because okay, let's see, then x2 will be greater than or equal to epsilon x1, which is epsilon square. So, this is okay, it's epsilon j, fine. So, therefore, you have shown that all xj's in any basic feasible solution, any feasible solution satisfying these constraints, the xj's will all be greater than or equal to the corresponding, I mean xj will be greater than or equal to epsilon j. So, therefore, so this implies therefore, all xj's will be present in every basic feasible solution. Okay. Now, you want to show that, so we say suppose second part of the lemma, suppose no Rj or Cj or Sj is present in a basic feasible solution, suppose. So, start with, so since R1 is equal to S1 is 0, this implies from the first 2 constraints, from here we get, this implies that x1 is equal to epsilon, and from here it says and x1 is equal to 1, but epsilon is less than half. Therefore, it is not possible, because epsilon cannot be equal to 1, but epsilon is less than half. So, this is not possible, right. So, therefore, either R1 or S1 is in the basic feasible solution, right. Now, look for the other, so now for any other j, for any other j, since rj is 0, you get from here that for another j, xj is equal to epsilon xj minus 1, right. And from the second constraint, you have, because sj is 0, xj is 1 minus epsilon xj minus 1, right. So, if you equate the two, these two together imply this equal that twice epsilon xj minus 1 is equal to 1. But remember, xj minus 1 cannot be, epsilon is less than half, right, because we started with the assumption that your epsilon is strictly less than half. So, in that case, this is okay. Where do we assume that xj's are xj's are less than or equal to 1 minus epsilon xj minus 1. So, xj minus 1 are non-negative, epsilon is positive. So, this xj is less than or equal to 1, right. So, this, and since xj minus 1 is less than 1, less than or equal to 1, and epsilon is less than half, this cannot be satisfied, right, because the product has to be equal to 1. So, therefore, either rj or sj has to be in the basis for all j varying from 1 to d. So, this proves this lemma, and yeah, and now another simple lemma I want to show you before I go to the main theorem. So, today I have tried to introduce you to a little bit of complexity theory, and where I am telling you what it means to talk about the time taken by an algorithm, and normally you would do it for the worst case. So, that you are sort of giving a upper bound, and the time for that algorithm cannot go beyond the worst case analysis that we do, right. Okay. Now, the second lemma is lemma 2. If S, okay, now I would like to give you a definition. So, I will do it afterwards. If S and S prime are two subsets of the set of 1 to d, are subsets of d such that d belongs to S, but d does not belong to S prime, then, and I will give you the definitions, I should have given them earlier, then we will say that x s d is greater than x s prime d, and if S is equal to S prime union d, that means d index was not present in S prime, and S and S prime differ only in the index d, then x s d is equal to 1 minus x s prime d. Now, let me explain first. So, in the before the proof, see what we are saying is we will for okay, for S a subset of 1 2 to d, we will define, we will denote x s as the basic feasible solution in which R j belonging to S are part of the basis, are in the basic feasible solution, are in the basic feasible solution. Okay, let me explain. So, what we are saying is that, you see, as this lemma says that either Rj's or Sj's have to be in the basis, in a basic feasible solution. So, what I am saying is now that you take some subset of these d numbers, and then you decide, you say that those the indices which are present in S will correspond to the R j's which are in the basis, in the basic feasible solution, right. So, R j, j belonging to S, right, and then and we will say that the corresponding basic feasible solution is denoted by X s. That means, in X s, for example, if I simply say X 1, then this means that this is a basic feasible solution to the system in which R1 is in the basic feasible solution. That means, for the remaining 2 to D variable indices, S1 Sj is present, right, and so R2, R3, Rd are all zeros if you consider the basic feasible solution x1, right. Similarly, if you consider the set x2, then that means R1 and R2 are in the basic feasible solutions, and then S3 onwards are in the basic feasible solution. So, this is the idea. Okay. Okay. So, subset of this. So, now what we are saying is here that the lemma says that if S and S prime are two subsets of this, such that D is present in S, but D is not present in S prime, then the corresponding X, and so XS D is the value of, okay, and okay, so XJS is the this needs to be, we need to go slowly. So, there is the value of Xj in Xs. So, this with this definitions, the lemma is now clear that if S and S prime are two subsets here, such that D belongs to S, but D does not belong to S prime, then the corresponding XSD value in the basic feasible solution XS, the value of the dth component, is greater than XS prime D. So, this proof is not difficult. Let me just quickly show you. Yeah, I would like to keep this here. So, we will so proof. So, we are saying that D is in XS, but D is not in is in S, but D is not in S prime. So, therefore, what do we have from here? That means, for the D, for j equal to D, SD is 0. So, since SD is 0, this implies from the last constraint that XD minus epsilon, or plus, sorry, plus epsilon XD minus 1 is equal to 1. So, which that is XD is equal to 1 minus epsilon XD minus 1, right, and this quantity is less than half, as I have been showing you already, right, because epsilon is less than half, XD minus 1 is also less than or equal to 1. So, this quantity, so minus will become greater, so which will imply that XD is greater than half. Okay, I should continue writing this, otherwise it will be confusing. Okay. So, that means, I have shown you that the value of XSD when D is present in the set, corresponding set S, is going to be greater than half. Okay. Then I want to show that this value is greater than XS prime D. So, now since D does not belong to S prime, this implies that your XS prime D is equal to epsilon X D S prime minus 1, which is less than half. Right. We are always saying that because epsilon is less than half, so this is less than half. So, therefore, you immediately get this implies that XSD is greater than XS prime D. So, first of all, I just want to point out that when I stated this lemma, I did not actually mention that this will be valid only when S prime is not empty. So, we should not try to see if it should I mean, we should not apply it if in case S prime is empty. Okay. Now, to prove the second part, that when S is equal to S prime union D, then XS D is exactly equal to 1 minus XS prime D. We want to prove this. So, I am using the, see, since S and S prime differ only in the element D, therefore, all other elements are the same. So, therefore, the values of the variables will also remain the same up to d minus 1, because they differ only in the dth component. So, x s d minus 1 is x s prime d minus 1, right. So, now and since d does not belong to s prime, that means R d is 0. So, here you will see that R d is 0. So, you get that x s prime d is equal to epsilon x s prime d minus 1, right, from here, because R d is 0, since d is not in s prime. And but we have just seen that x s prime d minus 1 is the same as x s d minus 1. So, this becomes epsilon x s d minus 1, right. Now, this number I write as 1, so I add and subtract 1. So, this is 1 minus of 1 minus epsilon x s d minus 1, but then this is because d belongs to s, therefore, s d is 0, right. And so, from here you will get that x s d is 1 minus epsilon x s d minus 1. So, x s d is equal to 1 minus epsilon x s d minus 1. So, I write x s d here for this number. So, this becomes 1 minus x s d, right. So, therefore, x s prime d is this, which you can write either way. So, you can bring x s d on this side, then it will be x s d is equal to 1 minus x s prime d. So, this is the relationship. And so, you see that when I prove the lemma 3, then you will see the connection, that you will actually be able to show that you can, as you move from one extreme point to another, the value of the objective function, that means the dth component is increasing, right, and therefore, you will follow a monotone path, and that the length of that path will be exponential. So, let me continue with the proof of showing why simplex algorithm is not polynomial time. So, now lemma 3 is that the subsets of 1 to d be enumerated in such a way that you can order the value of the dth component. So, S1, S2, S2d, because a subset having a set having d elements will have 2 raised to d subsets. We all know that, right, including the empty set, right. So, it will have 2 raised to d subsets, and let me call them S1, S2, S2 raised to d. So, this 2 raised to d is the suffix here. This is right. So, then you have ordered them in such a way with respect to the value of the last component of the corresponding basic feasible solution, right. So, given a subset here, as I told you how we can construct a basic feasible solution, and so in the basic feasible solution S1 x S1, this is the last component, the dth component of the basic variable, and so you have this. Suppose you have this enumeration, then the inequalities are strict. In fact, see, the values will keep on increasing strictly, and the basic feasible solution x s j and x s j plus 1 are adjacent, right. So, these two bases are adjacent the way you order, and so this happens for up to 2 raised to d minus 1. This is the lemma. So, let us prove, and we will prove this by induction. So, the proof by induction on d. So, okay, I'll need the formulation. So, suppose d is equal to 1, right. Then see, remember your constraints, I'll just rewrite them again, so that you might yeah, okay. So, this was x1 minus r1 equal to epsilon, x2 plus s1 equal to 1, right. Then we had xj minus epsilon xj minus 1 minus r1 was equal to 0, right, right, and then you had 1 minus, so, and xj plus epsilon xj minus 1 plus sj sj equal to 1, right, and all xj's, rj's and sj's, sj greater than or equal to 0 for all j. These were your constraints, right. Okay. So, for d equal to 1, you see only this is x1. Okay. So, you see what are the possibilities, because you have only one element, your set has only one. So, what are the two possible subsets? Either, so S1 is the phi set, right, and S2 will be just containing 1. These are the two possible subsets when your set has only one element, right. Okay. So, so corresponding to this, what will you have? Because R1 is 0, and so X1 is S1 will not be 0, R1 is 0. So, X1 is equal to epsilon. This will imply that your of course R1 is 0, and your S1 will be from here 1 minus epsilon. So, the corresponding extreme point is, or the extreme point will be what? Epsilon, then 0 and 1 minus epsilon, right. And for S2 equal to 1, R1 is there, S1 is 0. So, then X1 becomes 1, right. So, X1 is 1, and that gives you R1 as 1 minus epsilon, and S1 is 0, right. So, the corresponding extreme point here is 1 minus epsilon and 0. So, you see here the value is increasing. Remember the lemma 2, we said that, see, because D is 1. So, S2 contains D and S1 does not contain D. So, the component the value of X1 will be higher for this one than this one, which you can see that here X1 is higher than 1 is greater than epsilon, right. So, I was just, after obtaining these two extreme points when D is equal to 1, I want to show you that the lemma is valid, because you see we said that the values must keep on increasing. So, here you see this one is epsilon, and this first component is 1 here. So, this is satisfied, and since lemma 2 is not valid when S1 is empty. So, therefore, the point that this should be equal to 1 minus of this is not valid, right, because your starting set S1 is empty. So, that part will not be satisfied by this lemma, because the conditions are not met, but otherwise the values are increasing. So, now let us go to for D equal to 3, for example, and this is a perturbed cube that we have been looking at. Okay. So, here I just want, but before that I want to show you that the two extreme points are adjacent. That part we have to show still, right, because then the inequalities are strict, and the basic feasible solutions XS j and XS j plus 1 are adjacent for j varying from 1 to d minus 1, and so that part I want to show you. So, the two extreme points are adjacent. Why? Because let us just first define this notation, that AJs are the columns corresponding to the XJs in your constraint matrix, Bjs are the columns corresponding to Rjs, and Cjs are the columns corresponding to Sjs. So, for the extreme point epsilon 0 1 minus epsilon, when S1 is empty, then R1 is 0, right. So, in that case therefore, your solution comes out to be X1 is epsilon, and from here S1 is 1 minus epsilon, and R1 is 0. So, this is the extreme point. So, the corresponding basis is A1 comma C1, because you have two constraints when D is equal to 1. So, this is it. And for the second extreme point that we obtain, see here R1 is present in the basis. So, therefore, S1 is 0. So, X1 is 1, right, and X1 is 1, then your R1 becomes 1 minus epsilon, right. R1 becomes 1 minus epsilon. So, that is 1 minus epsilon and 0, and so this changes because now R1 is in the basis. So, you have the column B1 according to our notation. So, these are the two bases and they are adjacent, right. Only C1 has been replaced by B1. So, I want to stress this point, and therefore, the two extreme points are adjacent, the two bases are also adjacent, right. Now, for D equal to 3, if you go for D equal to 3, then I just picked up these 2 points and extreme points, and you can then verify the theorem for other points also. So, here for example, the point C is epsilon 1 minus epsilon, and you know that this point is actually 0 1 0. So, I will take R2 to be that means R2 will be in the basis, the corresponding set S I will take as 0 1 0. So, then R2 is in the basis and R1 and R3 are 0. So, if R1 and R3 are 0, then you have x1 equal to epsilon, right, and then from these two again you can just solve, and we have done this exercise already. So, this will be the corresponding, because I am just showing you the 3 coordinates, not the R1, that of course you can fill up. So, then the corresponding basis will be A1, A2, A3, and then since you are see here okay, C1 B1 comma B2, and this is C1 is R1 is 0. Oh, what point am I taking here? This is 0 1 0. So, I think what I have done is I am taking the point, because B1 B2 means that R2 and R3 are in the basis. So, that means and R1 is 0. Oh, so this is not the same point as that one. Maybe I can just remove this. Maybe it should not be misleading. Yeah, okay. Okay, just without the figure, do it without the figure. So, anyway, this is R1 is 0 and R2 and R3 are in the basis, basic feasible solution. So, then correspondingly what will be the point when R1 is 0, we are saying x1 is epsilon, and when R2 and R3 are there. So, for example, for x2, the component x2, this is 0. So, it will be 1 minus epsilon, right. And then again since S3 is 0, it will be 1 minus epsilon of x2, which is 1 minus epsilon of 1 minus epsilon. So, 1 minus epsilon plus epsilon square. So, this is the thing. So, I did not have the right figure there anyway. So, these are the bases, right. So, I said that E is the point which corresponds to 0 1 1, right. So, I had R2 R1 as 0. R1 as 0, and then S2 and S3 are 0. So, R1 0 gives me immediately x1 equal to epsilon, which I got here, and then you can immediately see that because S2 and S3 are 0. So, 1 minus epsilon square, no, it will be yeah, this will be 1 minus epsilon 0 1 1, yeah. So, this is epsilon, and then this will be 1 minus epsilon will come when you have okay. So, I am writing the point 0 1 1. So, this will be when R1 is 0, you have x1 epsilon. So, then x2 would be, and because S2 is 0, R2 is there in the basis. So, S2 is 0, therefore, this is 1 minus epsilon square. Okay, this is 1 minus epsilon square, and then the third one when S3 is also 0. So, it will be yes, because S3 is 0, and so yeah, for this one only R1 is 0, and then you have S2 equal to S3 is 0, right, for this point. So, therefore, this will be then 1 minus of epsilon times 1 minus epsilon square. So, this will become. So, let us just go through these points. For C you see you have R2 is there in the basis, and R1 and R3 are 0. Okay. R1 and R3 are 0, which means that then S1 and S3 will be there, if you remember the lemma. So, R1 is 0, see from here you immediately see that R1 is 0, then x1 is epsilon. So, I am going for the point C right now, right, and then what you have is that S2 is 0. So, from here you see x2 will be equal to 1 minus of epsilon x1, and x1 is epsilon. So, 1 minus epsilon square, right, and then again what you have is R3 is 0. So, if R3 is 0, you get x3 equal to epsilon of x2, which is epsilon of 1 minus epsilon square. So, epsilon minus epsilon cube, right, and so the corresponding basis is this, right, because R1 and R3 are not there in the basis. Then for the point E, I am trying to show you here again you see C1. So, R1 is 0, R1 is 0, therefore, x1 is epsilon. Then you again have R2 and R3 are there in the basis. So, S2 and S3 are 0. So, if S2 is 0, you immediately get 1 minus epsilon square, which is okay, and then again you get 1 minus. So, this is 1 minus epsilon square, then since S 3 is 0, you get that x 3 is 1 minus epsilon of 1 minus epsilon square. So, this is 1 minus epsilon plus epsilon cube. This is the calculation. Okay. And so, this is the basis, and you can see that immediately they differ only in. So, this is B 2 and this is, so they differ in B 1 and C 3. Okay. Because you have, oh yeah, you should write B 2 and this is B 3, sorry. So, this is B 2 and B 3. So, B 2 is there and B 3 C 3. So, they differ only in one column and therefore, they are adjacent. So, I just thought that I will, through an example, I will show you this part of the that they are adjacent, but of course, you can exactly in the same way do it for any j, and you will be able to show that these two bases will be adjacent bases. Now, suppose we will assume that the suppose the lemma holds for d equal to k. Okay. Suppose the lemma holds for d equal to k, which means that I can enumerate the subsets here, 2 raised to k subsets with this property, and the corresponding these things are adjacent and so on. So, suppose the lemma holds for this. So, now consider k, d equal to k plus 1, right. So, the thing is that S 1 to S 2 raised to k are also subsets of 1 to k plus 1, right. They are also subsets of this, right. And so, this property holds. So, up to 2 raised to k, these the values will satisfy this, because they are the same subset as they were there, right. Now, and so therefore, by the induction hypothesis, x 1 d plus d sorry, or should say k plus 1, right, because now that I have added k plus 1. So, that is the last component. So, this for these subsets is less than x s 2 k plus 1 and less than x s 2 raised to k plus 1. So, up to this is okay, right, by the this thing. Why? Because you see the sets S1, S2, S2 raised to k, when they are subsets here, they do not contain k plus 1, right. And so, then why should I be able to say this, and why should this hold? Since k plus 1 does not belong to x s j varying from 1 to 2 raised to k. Therefore, x s j k plus 1 is equal to epsilon x s j k. Yeah, right. So, again from here only, because the if you consider the set of constraints for j equal to k plus 1, then for k plus 1 you see this is 0, because all these subsets do not contain k plus 1 component, and so x j is epsilon x j minus 1, right. So, that is what I am saying, x s j k plus 1 is epsilon x s j k, right. And since these are ordered, so epsilon is a positive number, so these will be also ordered same way, right. So, this is fine. Okay. Now, let us consider, because we must have 2 raised to k more sets. See, this one, this has the number of sets is k plus 1, which is twice 2 raised to k. So, I have already taken care of 2 raised to k subsets. Now, you need more. So, obviously, you are going to add k plus 1 to each one of them, right. So, these 2 raised to k subsets you have, and to each of them you will add k plus 1. So, we will define, we will say that your set S j prime, let us call it, is equal to S j union k plus 1. So, that means I am numbering them again 1 to 2 raised to k. So, but there will be 2 raised to k in number. So, they together with these 2 raised to k subsets will form 2 times 2 raised to k subsets, right, okay, which is what we need. And what more? Yeah, so now here I need to order these remaining, the new 2 raised to k subsets that I have formed out of those. So, I need to order. Now, see, we need to see this here that yes, if you look at x s 2 raised to k plus 1, and you look at x s prime 2 raised to k plus 1, then you can see that this is less than this. Why? Because remember the lemma that I just did before this one. What is the difference between these two? S 2 raised to k is here, and yes, and x s prime 2 raised to k, this contains k plus 1 and this does not contain k plus 1. Therefore, this holds, right. And you also have, and that this is equal to 1 minus x s 2 raised to k k plus 1 by the same lemma, right. Fine. So, that means in this one here I can include this. So, here that means I am saying this is less than x s prime 2 raised to k plus 1. Fine, that part I have already shown you. Now, what is happening is that when you look at x s prime 2 k minus 1. See, remember the numbering of the sets is, see, you have s prime, where am I writing the things? Okay, this is 2 raised to k, the numbering is s prime 2 raised to k minus 1 and so on, and then you will have s prime 1. So, this is how you have 2 raised to k new sets, and we are just trying to order them here, right. So, now if you look at x s prime 2 raised to k minus 1, then this will be equal to, by the same thing what we have done is x s 2 raised to k minus 1 k plus 1 k plus 1. See, you just need to go slowly through the proof again and then you will follow it. Now, see, this is 2 raised to k minus 1 k plus 1 is less than, by this ordering, see, the x s raised to 2 k minus 1 k plus 1 is less than this. So, when you do 1 minus, yeah, this will be greater than 1 minus x s 2 raised to k plus 1, and so you have the ordering that this number is bigger than this. So, therefore, I will write this here x s prime 2 raised to k minus 1 k plus 1 and so on, and so you will finally reach to s prime 1 k plus 1, and that is your ordering. And the adjacency part also you can immediately do, because see, what is happening is that all these are adjacent, all these are already adjacent. Now, in the primes you are adding d plus 1, the k plus 1 column, that means r k plus 1 is the new variable that is a part of this basis, and so the adjacency continues, and so really one does not have to spend time on that. So, you should be able to. So, I think the lemma, so you have shown that you can, if you have the ordering for d equal to k, you have the ordering for d equal to k plus 1, and so you have demonstrated. That means what we have done is, so we have demonstrated essentially, yeah. So, we have exhibited, I mean, the lemma, according to me, the proof of the lemma is over, because the adjacency part is already been shown. So, I needed really to show you that if the ordering of the subset is there for d equal to k, then it is for d equal to k plus 1, and already I have shown you that you can order them for d equal to 1. So, therefore, by induction hypothesis, the lemma is over, and we have exhibited an exponential sequence of vertices for which the values of, and of course, they are adjacent, sequence of adjacent vertices, I should say, adjacent vertices for which the value of the objective function is constantly increasing. Okay. So, the idea behind this was that you should get familiar with the kind of things that are surrounded with linear programming problems. So, once we have exhibited this, we cannot claim that the simplex algorithm will be is a polynomial time algorithm. So, that is one thing. And what else we can, so basically, yes, this was the idea. Now, while going through this proof, I came across, I'll give you the reference, which I have already been referring to, that book by on linear programming, where they have transformed the problem. See, the corresponding linear programming problem here, which was maximize xd, right? They have transformed this into a form where you can actually show that the basis corresponding to this, find this, that means your xs prime 1, actually all the Cj minus Zj's will be non-negative, which is your optimality criteria. And the value, of course, is maximum. Yeah, and another thing, yeah, just want to point out one thing more here, is that, see, you started with this. If you remember the diagram I had drawn you, see, that was your the d cube. So, remember, this was this. This was the thing. So, we actually, okay, this. So, we actually started from here, then went here and this here, but you see, and this was your maximum point. So, actually you can show that if from here to this point, they also are adjacent. They differ only in one this thing, because from x s1 k plus 1, you can go to here. That means from, sorry, what I mean is that from the basis xs1, basic feasible solution differs from xs prime 1 only in Rd. In this case, of course, it's Rk plus 1, but in the general case for the d cube, it differs only in this. So, I could have in one iteration gone from here to here. I could have, if I specified the maximum improvement in the objective function value, okay, which in the simplex algorithm we don't do. We simply go by Cj minus Zj. But you could have done it and could have avoided this long sequence of pivots. But then some people have also constructed an example where they have shown that even if you specify the rule that the that you go for the maximum improvement in the objective function and then enter the variable, even for those they have constructed an example to show that there would be a long sequence of exponential pivots. So, therefore, it has been sort of established that simplex algorithm is not polynomial time. Okay. And so, that is one thing. And then, yeah, so I was talking about, I will give you the reference. They have transformed this problem to show that you can actually see the basis, and you can see the change in the objective function value, and you can show that your that Cd minus Zd is less than 0, continues to be 0, less than 0, because that is an improvement thing. No? If this is less than 0, then you will enter it. So, actually for all these bases, it continues to be less than 0, well, in this case here, right. But then because we want to show that the simplex algorithm has not actually specified the choice of the entering variable. So, you can try to be nasty, and you can use this long sequence of pivots and then arrive at the optimal solution. So, that way it is quite interesting example that they took some time, the Klee and Minty, to construct this. So, let me just write down the references for you, okay, and for this particular material. References. So, this is one is linear programming this is GB Danzig. I think for the interior point method I gave. So, this is basically for interior point method, Danzig and MN Thapa. This is for interior point method. So, and this is right. So, this is for interior point, and the other one that I want to give you for this is for Karmarkar and Khashian. Khashian linear programming of Wiley. This is okay. Bazara and Jarvis. For Karmarkar and Khashian, I would like you to also go through this material. Has been done by he has tried to make the authors have linear programming, the book linear programming and network flows by Bazara and Jarvis. And the third one is, yeah, and then I thought that this particular treatment, why simplex algorithm is yeah. So, okay, let me see. Bazara and Jarvis, they describe Karmarkar and Khashian algorithm very well, and they also have a different, as I told you, by transforming the problem, they show you why simplex algorithm is non polynomial. Okay, so for both the topics, this is a good book, you can go through them. Then finally, the treatment that I gave you here is from so this is 3 combinatorial optimization, that is the title, algorithms and complexity. Algorithms and complexity. This is CH Papa Dimitro and K Steiglitz. He has translated it from Papa Dimitro wrote it in Greek. It's been translated by the this, and so here this is the treatment. Yeah, and let me just quickly make the correction here. Why this was an error? No, this is okay. Epsilon and 1. So why is it not holding it here? The part that it should be equal less than 1 minus epsilon is 1. So anyway, this calculation is okay, and okay, fine. So later on maybe I'll add the correction if necessary. But finally, just want to say that I hope that you will find, when you have gone through all the lectures, you will have a good view of linear programming theory, its practices, its applications, and the other variations and the related new developments in the area, and I hope you enjoy the course. Thank you.